morning to introduce my advisor, Dr. Charles Kemp. Charlie is a primary faculty and associate professor here in the Department of Biomedical Engineering, but also holds adjunct appointments to the School of Interactive Computing and Electrical and Computer Engineering. Charlie got his bachelor's, master's, and doctorate all from the Massachusetts Institute of Technology, where his dissertation was under the well-known roboticist Rodney Brooks. Since then, he's come to Georgia Tech, and in 2007 founded the Healthcare Robotics Lab. As the PI of the Healthcare Robotics Lab, he has directly advised students from VME, Mechanical Engineering, Electrical and Computer Engineering, Industrial and Systems Engineering, and from the School of Interactive Computing, all with the broad goal of advancing real robots to provide assistance for real people. Now, his work has resulted in, I believe, 11 journal publications, somewhere in the neighborhood of 50 conference papers, wide coverage in the popular media. Any three-letter acronym you can come up with has come by at some point. Lots of great stuff, and in 2012, the NSF Career Award. Now, his work that is so great and exciting has involved things like robots fetching objects for people, opening doors and drawers, reaching in really dense clutter, but also having people actually reach out and grab robots, which has led to people dancing with robots. And in addition to that, we've had robots touching people, and then robots shaving people, and then more robots touching people. And somewhere in all of this, Charlie has probably the unique distinction of having actually been shaved by a man with quadriplegia, controlling a robot from over 2,500 miles away. So, without further ado, to try and explain all of this and tell you why it really matters, Charlie Kemp.
Well, thank you, Phil. I would recommend you as a introducer for anybody. That was excellent. Thank you. All right, so I'm Charlie Kemp, and I won't introduce myself any further. So right now, I want to provide a little bit of context, because this is going to be a talk which in some sense is from the proverbial fire hose. I have a lot of information, and my hope is that you'll just get a better sense for what's happening in robotics broadly, what's happening in robotics in terms of healthcare, and then also some of the research that my lab has conducted. So in terms of robotics broadly, there's a major transition that's happening right now, and that's that previously robots were primarily successful in factory settings. And some things that distinguish factory settings are, one, that people tend to be kept away from the robot, and another is that those settings can be very predictable. So the robot doesn't have to be that intelligent, or at least the type of intelligence it has is very different from the type of intelligence we have and other organisms have when working in these more unpredictable environments. And the big transition that's happening right now, we're in the midst of, which is really exciting, is robots moving out of these controlled settings into human environments like homes and healthcare facilities, where they're working closely with people and where the surroundings are unpredictable. Now, this sort of transition introduces lots of challenges, but of course it also introduces lots of opportunities. And so I'm going to be talking about this sort of transition in the context of healthcare. And specifically, in my lab, we focus on a particular type of robot, and that's called a mobile manipulator. And what distinguishes a mobile manipulator from other types of robots is that it's mobile, in our case wheels. It allows it to navigate within the environment as an independent entity, and then it also can apply forces to things and manipulate the world, in our case frequently with arms, and often human scale. Many of these are robots from my lab, some of which we've built, some of which we've just purchased. These robots have arms and they're able to manipulate, mobile manipulators. And the problem that we focus on is health-related physical assistance. And people have, millions of people across the world have physical disabilities, and those disabilities can be from a variety of reasons. They could be age-related disabilities, they could be due to illness, they could be due to disease. For example, in the US alone, you have about 250,000 people with spinal cord injuries, and then of course a growing problem in the worldwide really is that demographically societies are aging. And so with age tends to come physical impairments, so that's also a looming challenge. We also work with people with ALS. There are fewer people with ALS, but that's another place where we think robots can make an impact. So right now, in terms of providing physical assistance, biology really is the solution that we rely on a day-to-day basis. And in particular, mobile manipulators. People typically provide this sort of physical assistance. They could be nurses, they could be professionals. They often, for people with severe disabilities, a lot of the assistance will be provided by an informal caregiver, such as a spouse or other family member. But there are other examples that are a little bit more exotic of biological mobile manipulators providing assistance. This is a service dog at Georgia Canines for Independence. This is actually the proprietor of the organization. So she doesn't have a disability, but she is directing the dog through gestures and speech, and the dog is actually quite dexterous and able to help in a number of ways. This is more exotic. This is from Boston, Helping Hands. It's a monkey helper. Person's directing the monkey with the laser pointer, and then the monkey's able to infer what it should be doing to provide assistance based on the location of that laser pointer. And this actually inspired some of the initial research that we did in my lab. So we have good assistance. People provide very effective assistance for others. So there's a question of why robots. Well, one issue is there are a number of looming healthcare challenges, and some healthcare challenges that are really here today. One aspect of this is just that it's a very long wait. If you want a helper animal, you have to wait many years on this waiting list in order to obtain that help. And there's also a high cost. Even for like a helper monkey, it's about $30,000. And then for example, for a certified nursing assistant, 40 hours a week, that would be about $24,000 a year. More importantly, there are shortages of healthcare workers, direct care workers, and those shortages are increasing, and that's a problem worldwide. Part of that is because of aging. And then finally, if you can imagine, as these shortages occur, it creates problems. And one aspect of that problem is that as you have to take care of more people, if you're a nurse, the quality of care tends to go down, and it's more likely that you'll actually leave your profession. So there's some of the challenges, but there's also, robots offer opportunities. And this is just a short list of some of the things that I think robots have to offer for healthcare. One, which we've seen a lot with the people we work with, is that robots can provide a sense of independence. It gives you the potential to feel that you're doing things for yourself. It empowers you to do things for yourself in a way that having a human assistant won't necessarily do. And also, in some of the research we've conducted, in particular with Professor Wendy Rogers in the School of Psychology, we found that actually older adults would prefer robots for some forms of assistant than human assistants. So there actually are some perceived advantages from people who would be using this technology. Another is the potential for extreme vigilance. So a robot has the possibility of helping 24/7, providing personalized assistance in a manner that an individual human providing assistance just wouldn't be able to deliver. Also, because it's potential for general purpose technology, you can benefit from economies of scale as the technology advances, and the economics should be nice, it should work out. And then finally, and this is sort of the thing that I like to emphasize, we're really at the beginning of this. So we don't really know where this technology is going to lead. There's a tendency with new technologies to think in terms of what is being supplanted, what is being replaced. So if you look at, for example, cars, the first cars, anyone know what they tended to look like?
Horse carriages.
Horse carriages. They did tend to look like horse carriages. And it was only over time that they evolved and were designed to really take advantage of their distinct capabilities. And the same thing with robots. Just as an example, robots have ESP. They can communicate digitally to one another wirelessly. They can also talk with the cloud. They can also replicate one another perfectly, at least in terms of the digital capabilities, and pretty precisely in terms of the mechanical properties. Those are just a few examples of ways in which robots are really different. They're different. Another way is a robot can, many robots, can hold an object up indefinitely, whereas you or I, we would get tired and we'd eventually have to move the object down to rest. So there really are differences, and it's going to take time for us to understand what the implications of those differences are for healthcare. So that's sort of robotics in general, but why mobile manipulators? That's another natural question, because there are lots of forms that robots can take. And there's a natural meshing here, a complementary aspect of robotics and people with impairments, because robots can move, and if you have deficits in terms of motion, then the robot naturally can sort of help you overcome some of those deficits. And these are some examples of other forms that robots take. For example, prostheses, exoskeletons, wheelchair-mounted robot arms, or this desktop robot, which is specialized for assisting people with feeding. So it's a natural question, why mobile manipulators? And these are some of the reasons why I think mobile manipulators are something that are particularly important to investigate right now in the context of healthcare. One is that they can operate independently from the user. You can task the robot to go do something, and you don't have to go along with it. Another is you don't have to put it on and take it off in the morning. So right now there's a lot of emphasis on exoskeletons, these wearable robots, But what I believe will be a serious barrier to acceptance is the need to put it on and take it off. So for example, for older adults, even something like a technology of just a necklace with a button that you press if you fall, it's difficult to get people to actually wear that on a daily basis. So there could be challenges for some people convincing them to actually wear a robotic entity. Right? Another aspect of that is less encumbrance, and from that, as an example, for wheelchair-mounted robot arms, a common complaint is that it expands the effective size of the wheelchair and makes it more difficult to maneuver and to move that wheelchair places. Also, for Mobile Manipulator, it has a potential to be a shared resource. So you can imagine that at a living facility where there are lots of older adults, all of them can benefit from this same robot, which I think is going to be important in the beginning because the costs are relatively high for this technology at the moment. There's a possibility of performing a wide variety of tasks. Unlike, for example, that desktop robot that feeds someone, this type of robot, with the proper programming, can perform lots of different tasks and also help a variety of end users in lots of different circumstances. So as you'll see in the rest of my talk, it can help someone who's in bed, it could help someone that's ambulatory, who's able to walk, it could help someone who's while they're in a wheelchair, whereas a number of the other technologies are much more specialized and are less general. And then finally, related to that, it's suitable for commoditization. And to me, I think this is one of the most exciting aspects of this type of technology and this particular type of robot platform. Unlike a lot of those other robot platforms, this is a general purpose type of robot. So the best analogy I can think of is if you look at the personal computer revolution, it made a tremendous impact in healthcare and also made a really large positive impact on the lives of people with disabilities. And it's not because it was a specialized assistive technology or medical device, it's because it was such a general purpose technology that the economies of scale played to its advantage, and then it could be repurposed into these sort of healthcare settings. There's a typical challenge in medicine and healthcare where specialized technologies only serve a small niche group of people, and the costs tend to be outlandish. It's kind of shocking if you go and we bought, for example, an assistive joystick, and it's a simple joystick. You think it'd be like a Nintendo thing, and it's thousands of dollars, right? And so this has the potential to be like that personal computer, to be a general purpose robot that can be used in lots of different circumstances. Ravi Bellamkonda, Professor Bellamkonda, likes to talk about a robot in every home, and I think that's actually a reasonable projection of the future. Robots like this can potentially be ubiquitous, and based on that, the costs will be reasonable, and then healthcare is one place where they can make an impact. So since 2007, my lab, we have worked hard to work with potential end users. We've worked with over 200 people in collaboration with a number of others, labs, and with real robots. And so far, the results have been really surprising to me, at least. And I think to others in the robotics community about how accepting people would be and excited people would be about this type of assistance. So we've worked with older adults and nurses, able-bodied subjects, and in general, I think one thing I am confident of, given our research, is that there's no obvious impediment or barrier to people actually wanting this technology and wanting to use it, which is not, especially with older adults. There have been thoughts that maybe older adults would not be accepting of this type of technology. And now what I'm going to do is I'm going to give you a very brief overview of a lot of research we've done in my lab, just to give you a sense for things, and then I'm going to focus in on something. So this is the first robot we built back in 2008. It's a mobile manipulator. It was called Ellie, and we were focused on object fetching. So people with disabilities, there's the person here has ALS. This was in collaboration with the Emory ALS Center and Dr. Jonathan Glass. So there's a tendency when you're getting ALS, it's a progressive neurodegenerative disease, to drop objects and then not to actually be able to retrieve them. And that can be a very frustrating experience, as you can imagine. Because imagine we did a study and people were dropping objects about 5 times a day, and sometimes the object could be inaccessible and unretrievable for maybe 30 minutes to 2 hours. I think we had an example of someone not being able to retrieve an object for 2 hours. And people often feel like they are a burden to their loved ones because those are the people who will retrieve the object for them. So that's a fairly complex robot, and that was one example of what it could do. One thing I didn't note, which now it's actually pretty important, I guess. She's using a laser pointer to designate the object. So this was inspired by that the laser used with the helper monkey. So she's able to designate a 3D location, and the robot infers what it should do based on that 3D location that's been designated. So she designated the object, and then she designates herself. You can think about it as being virtual buttons in the world, and she's clicking on those virtual buttons. But we also wanted to look at the potential for a more specialized robot to do these things. Because one of the things we found was that for the top 25 objects that people would want to retrieve, people with ALS, that they were small and lightweight. So we were able to design this special hand for the robot that makes it really easy for the robot to retrieve objects. So in this small study at the Emory ALS Center, 20 people with ALS controlled the robot to go and pick up and retrieve an object for themselves. And one of the things I want you to focus on is the expressions on their faces, because although we have the quantitative data to support that this is something that they would really want, I think the facial expressions communicate quite a bit. Key aspect here is this robot has an intelligence, if you will, built into the mechanics of the robot. All the person has to do is use a joystick, and then there are two buttons. One button says pick up the object that's right in front of you, and the other button lifts up that object to an ADA recommended height. And out of the 60 trials, I think in 59 of those trials, people were able to retrieve an object. And for many of these people, they may not have been able to retrieve an object for quite a while. Other things that we've done more recently are shown in this slide. So for example, I mentioned we worked with nurses. If you look in the upper left, you'll see work where nurses were able to lead a robot by the hand. That robot was over 350 pounds, but they found by having this natural interface of leading by the hand, they were able to move it through a cluttered environment, a representative of a healthcare setting like a hospital, and then position it up to a patient's bedside. In the lower left-hand corner, that's work where we had able-bodied people come in and the robot acted as though it were a nurse. And we really want to just find out, would people be okay with a robot, an autonomous robot, coming up to them and making contact? One of the most interesting things about this work was that, first of all, people were fine with it, but it turns out that there's a critical detail that's important, which is what people's perceptions of the intent of the robot are. If the mechanics, it turned out, we had the mechanics controlled under two situations. But in one situation, people were led to believe that the robot was trying to provide comfort to them. In the other, they were led to believe that the robot was cleansing the person's arm in preparation for a doctor to come in. And that difference, even though the mechanics were the same, and in robotics, there's a tendency to get very focused on the mechanics. In fact, the latter part of my talk will focus on the mechanics. That perception made all the difference in terms of whether a person would be willing for that robot to touch them again and how they perceived that contact. So as robots become more autonomous, we're going to have to actually be worried about those types of things, which are interesting design issues. And then finally, well, on the right side, bottom right, this is research we did with Professor Wendy Rogers' lab, where older adults, we had a robot deliver medicine to them, using an RFID tag, and that was successful, and people were very willing to have this robot approach them, deliver medicine, would like that sort of technology. And then finally, in the upper right-hand corner, this is some of our most recent work. Professor Lena Ting is in collaboration with her lab and her, as well as Dr. Madeline Hackney. And we're looking at, could robots like this, using technology similar to what's in the upper left-hand corner, be useful for rehabilitative dance? And we had older adults come in, they danced with the robot, and there's some real reasons to consider this. One is that Dr. Madeline Hackney has shown through clinical studies that rehabilitative dance can be a very effective intervention. The other aspect of it is that, and one aspect of that is that it's fun, right? There's an aspect of motivation, and will people actually perform the task? And this is something that's become more and more prevalent and recognized within the rehabilitation community, is that motivation is a serious issue. You can have a whole series of interventions which are shown to be clinically effective, but you're depending on people to actually do those things. And if they're perceived to be boring or arduous, it's less likely that people are actually going to adhere to whatever the regimen is, and that you're going to see the desired effect. So I was actually really surprised. This is recent work, but the older adults that were in the study really liked it, and it was the simplest dance you can imagine. It was just walking back and forth. So I think they're, as strange as it is, and it's some of the more out there work, I'd say, is from my lab. And I'm sure Lena would probably agree, it's some of the more out there stuff for her lab. It actually seems very promising.
Could you just say which was preferable, the cleansing on the...
Sorry, yeah, good point. The instrumental task, what we would call the instrumental task. So if they perceived that if they thought the robot's intent was to cleanse the person's arm, And this is all mock. That's one of the other things that's strange. I mean, it's not like they actually needed a medical procedure. But if they believed that the robot was doing it to cleanse the person's arm, then they were fine with it. They much preferred that. Yeah, it was actually, had negative responses to a situation where they perceived that the robot was going to provide comfort for them. We modeled this actually based on studies with nurses. There have been studies with nurses where they've observed their observational studies. They've looked at the types of contact that occur between nurses and patients, and then they've classified based on the nature of that contact. And one of the major classifications they found in this sort of research is between what they would call instrumental versus effective. So is the touch there primarily to be some sort of emotional communication, or is it there to actually perform an instrumental task? And these observational studies have suggested that with human nurses and human patients, that instrumental touch is more preferred. And that in fact, there can be problems sometimes when the touch is emotional, which is also counterintuitive. I think I recently saw an article where people were claiming that unless robots can provide care, then humans are going to be preferred to them. And I don't think that's necessarily the case. In a healthcare context, it's not clear how often people really want that emotional touch. It really depends on what you're doing. But I should also say, I would not take that study and then say, that distinction, I would be wary of really emphasizing that too much. The thing to really learn from this is that the perceived intent is important. It's an important factor. But I would not want to suggest that robots can't provide useful care through emotional connection. In fact, there's some research to suggest that robots actually, that's something robots can do and that it could be beneficial. So, and one of the, I think the drawbacks of that, we didn't design this robot to be an amazing emotional support, an emotionally supportive mechanism. We designed that robot primarily for physical interactions. So you could argue that, well, it's because the design of the robot wasn't really optimized for providing comfort. So the real lesson is, as robots become more autonomous and they're interacting with people physically, these more psychological aspects and the perceptions of high-level aspects of agents in terms of their intent are important. And it's something that I think there's a tendency within engineering not to think of that, because that's a harder thing to model in a lot of ways. Does that do it? Yeah, okay, great. So for the rest of the talk, I'm going to focus on one body of work that we've been doing, and it's been with Henry Evans. So Henry Evans suffered from a brainstem stroke about 10 years ago, around the age of 40. This is his wife and primary caregiver, Jane. Unfortunately, because of that stroke, he was locked in for a while. Now he can move his head and he can move a finger. That's enough for him to control a computer. There's a head tracker, which he can use to direct the cursor, the mouse cursor, and then if you see down there, he can move a finger and click the mouse button. Unfortunately, he can't speak, though. And he saw me on CNN and contacted me and this company, and we began working with him. And through our efforts, we've done a number of things actually in his home out in California. This is a PR2 robot. This is an example of some of the work we've done. And what we did was we were able to automate the home. So there are these small tags that the robot sees. And in fact, we have these programming tools so that Henry was actually able to take the robot on a home and say, through his home, and say, this is a refrigerator, use this refrigerator opening behavior. And then based on that, after it's set up, a process that he can actually participate in, then he can just trigger the robot will autonomously navigate to the location and then perform the tasks such as opening the drawer, opening the refrigerator. But that said, what I'm really going to focus on for the rest of my talk is controlling forces and the importance of controlling forces as robots providing care. And I'm going to really focus this around Henry. So one way of dividing up tasks that robots would provide assistance with is into categories that have been used quite frequently in medicine and in disabilities research. So two main categories are activities of daily living, which tend to be these really important self-care tasks, which are really close to the person. Primarily 5 categories. You have feeding, toileting, transferring, dressing, and hygiene. That a person's ability to do these things is highly predictive of whether or not that person can live independently. And then another class is instrumental activities of daily living. These tend to be tasks that are farther away from the person in the house, things like housework, food preparation, shopping. Key aspect of these is that both of these types of tasks, manipulation is a really important aspect of them. And that's a place where robots, and in particular mobile manipulators, can help. One other thing that's very important about this is to note that for these tasks, which are especially important, these activities of daily living tasks, manipulation is near the person's body. And as I'll emphasize more as I go on, when you're manipulating around a person's body, regulating forces becomes especially important. So first of all, I'm going to talk about regulating forces at the robot's hand. So this is some work we did where we enabled Henry to shave himself for the first time in 10 years since his stroke. It's a specialized system for this, although aspects of it could be more general. It's a web-based interface. It starts out, he's able to drive the robot to his wheelchair. The robot positions itself in terms of a 3D pose with respect to that tag attached to his wheelchair. Then he's able to play back pre-recorded trajectories of the robot's arms in preparation for the task. And I should note, Henry is an expert user. He's able to do this in part because we've worked with him for so long, and in fact he's able to use these things and test things in my lab because it's a web-based interface. So it positions the mirror, it positions the electric razor. At this point, Henry helps the robot register a 3D model of his head to his head. So he clicks on a part of the face, then the robot uses a skin color model and the 3D point cloud is what you would call it, which it's sensing through a Connect sensor to fit a model of Henry's head to him. Now this is stuff, this is done in the lab in order to illustrate what Henry is doing. The nice thing is once the robot has that model fit to his head, he can then use these coarse, semantically labeled commands. He can say, move the electric razor to my cheek, move it to my chin. So it coarsely positions the electric razor near the requested body part, and then after that, he's able to finely position it with respect to an ellipsoidal coordinate system, which makes it easier because you can imagine if you're working in Cartesian space, keeping the orientation appropriate is not easy. So this simplifies him getting to where he wants to go. And now, what's especially important for the point I want to make about this is the robot also records the force, is sensing the force, and if the force goes above a predefined threshold, it retracts. And that turns out to have been very important. When we first started doing, actually the first time we tested this with Henry, an initial notion of a shaving system, he got these nicks and abrasions. And we were really surprised. We hadn't anticipated this. We then looked into it a little bit more and we measured, and he was applying, the robot's just holding the electric razor. I should emphasize that. So he was applying the force to himself. But we measured he was applying about 25 newtons to himself. Then we measured how much his wife Jane would apply to him, and it was about 3 newtons. So something seemed to miss. We went back to our lab and we conducted a small study where we had able-bodied participants shave themselves, recorded the kinematics and recorded the forces, and we found that you definitely do not need 25 newtons to shave yourself. In fact, to do entire shaving for all of the participants, no one required more than, well, certainly not more than 10 newtons, 8.2 newtons. So the robot, the other aspect of this that I want to emphasize is the robots are really dumb right now. Robots are stupid. Don't be fooled by the movies. They don't have any common sense. If you or I were to help Henry shave, I can pretty much guarantee you we would not allow him to apply 25 newtons to himself. The robot has no experience with these things. So this is an example of one way that robots can get, first of all, it emphasizes the importance of giving robots common sense, and with respect to forces, what are the forces that are reasonable in various circumstances? But also it provides a method by which you can do that. One example of a way to do it is to actually have able-bodied people do the task and quantify it, record the kinematics, record the forces, and then use that, the robot can use that as a model as to what is appropriate while doing that task. Long story short, once we took 10 Newton threshold and we implement it on the robot, and the robot retracts if Henry tries to apply more than 10 newtons to himself. Since we've had that, he has not had a nick or abrasion. It's been fine ever since. So a little bit of common sense can go quite a long ways. This is another example of common sense in a way that most able-bodied people would not think about this. And that's specifically with door opening. So if robots like these are going to be helpful, they're going to need to be able to open doors. That is important for moving from room to room. It's important for accessing objects that are relevant, because many objects are behind cabinet doors and such. And yet, it turns out there's kind of a trick there. And that trick is emphasized here. So what we did was we took a portable motion force capture system into Atlanta and captured the forces required to open lots of different doors and the kinematics associated with those doors. And what we found is that this is just the opening force, the initial force you have to apply in order to open that mechanism. And you see that spring-loaded door is about 60 newtons, kitchen cabinet is about 5 newtons. So the problem is, if there is no knowledge of this, if the robot doesn't understand this, doesn't have that common sense, then it has to either, if it, for example, had a fixed threshold, either it's going to be really conservative and it will only be able to open office cabinets and kitchen cabinets, or it's not going to be conservative at all, and it's going to be willing to apply 60 newtons to something like an office cabinet or a kitchen cabinet. So if this is locked or it's broken or something, the robot's going to apply a force that is completely unreasonable, something that you would never do, and it's not going to recognize that there's a problem. And when that sort of situation occurs, there's more possibility of something breaking or there being an injury. So what we showed is that if the robot has a sense of the general category, which is something that a robot could gain just by knowing, oh, I'm in a kitchen, or this looks a bit like a refrigerator, then it can have a much tighter bound in terms of the forces that it applies. And by doing so, recognize these anomalous conditions and halt if it's something that's a problem. It's also interesting, and one of the things I thought was exciting about this, what this shows is for this door up here, it shows the forces as a function of the angle of opening of the door. Actually, the tangential force. There's a circle that's traced out, a circular trajectory traced out by the handle, and this is the force that's tangential to that trajectory. So it's the opening force as opposed to forces that could be unbounded due to constraints. And you see that it's very consistent. Now this is opening the door slowly. You would call it a quasi-static model. You'll see that for the 2 different humans opening the door and 2 different robots opening the door autonomously over numerous trials, if you have the angle, you can do a good job of predicting what force it's going to be. One of the things that's cool about that is we showed, well, look, the robots can categorize the type of door based on these trajectories. If the robots open a particular door more than once, it can do a better job of detecting whether there's a collision or if it's locked or if there's some other anomalous condition. So it can actually learn to predict particular devices in the environment. Okay, so that's an example of regulating forces at the hand of the robot. But there's a whole arm here, and there's a whole body of the robot. And it seems plausible that those are also important to regulate. And an interesting aspect of robotics is that the dominant strategy for robot manipulation has been to avoid contact between the robot's arm and the world. So the robot is not supposed to touch its arm to the world, it's not supposed to touch its arm to its own body, and it's not supposed to touch its arm to other people. But that seems sort of strange to have that constraint in robotics, even though it's been so prevalent. And so we decided to look, at least in terms of helping an individual in a wheelchair, what do you lose when you make that requirement? What do you lose? And in particular, what we did was we said, let's look at the poses that the robot can achieve with its hand relative to this model of a person in a wheelchair. And we're going to see, as the robot is more conservative and keeps a larger distance between its arm and this model here, the person's body, how many poses does it lose? Because, for example, in that shaving task, all the robot did, fundamentally, was to position the tool with respect to the person's face. So there are large categories of tasks where a robot could provide assistance if it could just effectively position a tool with respect to the person's body. And what we found, this is an example of poses that are lost if you have just a 4-centimeter safety margin, which is sort of what you'd need to have if you wanted to avoid contact due to noise and the sensing and the actuation. But it's really dramatic. You have a 10-centimeter safety margin for this robot and this particular model. You lose about 50% of the poses that could have been achieved if you allowed contact. And this is even conservative because this is assuming that those are both rigid bodies and there can be no interpenetration. Whereas the reality is if I have clothing, the robot can move in a little bit and it's really no problem. And my body's a little bit compliant. So you actually are going to lose more poses than this. So that suggests that, it's pretty convincingly, I would say, that allowing contact between the robot's arm and the person would increase the available poses for the robot's hand. But that's fine, but if we can't actually achieve that safely, then it's an irrelevant result, at least in terms of the practice of healthcare and robotics. So once again, if we revisit what the dominant strategy for robotics has been, it's avoid contact. Okay, so now we're saying we don't want to avoid contact. How can we do that, or is that reasonable? Well, if we look in biology, if we look at people make contact between their arms and the world all the time. And it's not something that's considered some great feat of dexterity. It's just a general thing that we do. We do it subconsciously. We don't even think about it. Likewise, we make contact with our own bodies it's not a big deal. It's something that we do. If I look across the room, many of you are making contact with your own bodies. You have your arms folded. Yeah, thanks Ross for the counterexample. You have your arms on the desk. And then in particular, when we're providing assistance to one another, we tend to make contact between our arms and the body of the person who's receiving the care. There are also extreme examples. We don't need vision. We can just use a sense of touch. This is a New York Times reporter exploring a sport that is common in Georgia, apparently. And I'm trying to remember, noodling. It's called noodling. You reach into some hole and then you pull out a large catfish. And he gave us permission to use that picture in a journal article, which was a lot of fun. I think he was surprised. And this is an example of people going to get a clam, digging for clams. And animals also do this. I mean, animals make contact between their arms, and they reach into places where they can't really see what's happening. So they don't have, the thing I want to emphasize about these is that this person does not have a very clear model of what's going to happen once he or she reaches into this hole. Right? It's very much an unmodeled situation. It certainly can't have a precise geometric model, which is what many methods of robotics have relied on. And similarly, for these situations, if you're reaching under snow, or you're reaching into this little aperture, or you're reaching into this tree, you don't have a good model, and it would be sort of counterproductive to try to obtain a good geometric model of what the inside is, where you're going to be reaching. So we took inspiration from biology, and we said, look, there are two characteristics of these biological organisms have the robots could probably use to do a better job at this type of thing, or to achieve this. One is compliant joints. Now that's something that now is actually in commercial products and is pretty common. But the other thing which is remarkably uncommon, probably because of the evolution of robotics, in the sense that they were really optimized for factory settings, robots have not had force sensing across their bodies. And yet if you look in biology, from the millimeter scale to the centimeter scale to the meter scale, organisms are able to sense contact and contact forces across the entirety of their bodies. Something that robots haven't been able to do. Like these little hairs here on this ant, this is just showing human sensitivity to touch. And I think actually that even goes down to cells. You have mechanotransduction sensing even in cells. So it's something that's built in, and yet robots hasn't had it. So we made the assumption that we were going to have a controller that assumes, first of all, that low contact forces have no associated penalty. It's okay to make contact with the world as long as the forces are kept low. Contact is allowed as long as the force is low, and then we assume that the robot that's being controlled has low stiffness compliant joints and whole arm tactile sensing. And if we make those assumptions, that enabled us to make a new controller. Now this is what's called a model predictive control. And one of the things that's nice about model predictive control is it allows you to be explicit about how things work. And the way this works is that at every moment in time, the robot creates a simplified model of its arm in contact with the environment. And then it's able to say, okay, how can I change the equilibrium angles of these viscoelastic springs in my joints such that I'll get my hand as close as possible to my target location while keeping the predicted forces below a threshold. So this is a planar version of the model. Every contact it senses with the skin, it models as a simple linear spring. Then it has these are torsional springs at its joints, and it controls the equilibrium angle of them. It turns out that when you put all this together, you can, do some linearizing, you can end up with a quadratic program, which robots or computers are able to solve very quickly and to find an optimal solution. This is an example of how, just to give you a sense for how the control system works. This is the robot. For the joints, we are using simple impedance control. So you can think of that as having gravity compensating torques that are built in with the forward model of the weight of the robot. Plus, you have these viscoelastic springs at the joints. So this is the stiffness, this is the damping at each joint. And then that's running very quickly. That's at 1 kilohertz. You could implement this mechanically, but in our case we have torque-controlled joints, and so we're able to simulate those springs. Then on top of that, at 50 to 100 hertz, is where we're running this model predictive controller. So it's relatively slow, but it actually, while running on top of this, has very good behavior. So this is an example of the robot using this with this quasi-static model. So it's quasi-static because it's assuming that it can neglect the inertial torques and inertial forces. And so it's just trying to reach those green blocks. This is all it can sense about the world. It doesn't have any geometric model of the world. It just reaches into it, senses the forces, uses this controller to make sure that it keeps the force low. Listen. So I really love that because that's something that robots prior to this, at least I have not encountered any robot doing that. It really wiggled in there and it pushed, even though it had contact on both sides of it, something that the robot wouldn't have been able to sense just based on joint torques. It had to use its tactile sensing, and it really pushed in there, and it was fine. It still managed to keep the forces below the desired value and to reach that target. And we tested this in a number of other sorts of circumstances, including artificial foliage and cinder block. This is an example actually of our most recent work where the robot is using not just a quasi-static model, it actually has a model that incorporates a model of the dynamics of the arm, and therefore, based on that, it's able to move faster. And it also includes a model of collision forces. So it has a model that says, if I were to have unexpected contact with a rigid object, what do I think the forces would be? And based on that, to move quickly through an unknown environment like this while keeping collision forces as well as these contact forces that are persistent low. Okay, so that gives you a sense of the controller. That was funded by DARPA. That's why a lot of those examples were in other sorts of situations. For example, IED disposal is something that you'd want. But we also wanted to bring this back to Henry and see, would this be advantageous, as we would expect. To do so, we had to create tactile sensing for our robots. This is a tactile sensor we developed for the PR2 robot. You can see there. I won't go into the details because I'm a little short on time. The interface is just, actually it looks like this, at least one of the interfaces that Henry used and that he is going to be using in the video I'll show you in just a moment. He positions a virtual hand of the robot, and then he says go, and the robot does the best job it can to get there while keeping the forces low.
Henry Evans is talking himself in for the first time in 10 years. Evans became quadriplegic in youth after suffering a stroke in 2003. Now has limited use of only one finger. Evans is using a computer interface to control a uniquely specialized robot, one that has the ability to feel its way through tasks with a sense of touch.
Henry, what did you think of the robot with tactile skin when we tested?
These are very much prepared comments.
With software over a computer, Evans recalls his first physical interaction with the robot.
With the touch-sensitive skin, I could feel the robot keeping contact forces low, but still constant pursuit of its goal. I felt immediately that it would improve me, but rather it seemed aware of my presence as he went about his business.
So the long story short is that when we tested this out, Henry just wanted to get a sense of it on his wheelchair, and he got really close to it. And this was new because we've been working with him for about a year and a half. He had not felt very comfortable around the robot. He wanted to have distance between himself and the robot, except in very controlled situations. One thing you might notice about that shaving is that the robot's very careful about how it reaches around his body to put the shaver near his face. It's a very controlled sort of motion. And that was about all we could do where Henry would be comfortable. In this case, after having experienced it and worked with it in his wheelchair, the next day he's like, look, I just want to try it out from my bed. Let me just give it a shot and I'll do whatever I do. And he took it and he was able to reach underneath his little bedside table here, or overbed table, grab a cloth, wipe his face, and then do something that we had not been able to figure out how we were going to do, which is to pull up a blanket for himself. Which is sort of another example of these types of tasks that if you're able-bodied, you don't think about how important it is. You want to regulate your body temperature at night. You don't want to wake up your spouse to do it, right? So this is something he wanted right from the beginning, but we didn't know how he would do it. And you can see why, because it's, at least with this robot, it's not clear how you would actually go about doing this without making contact with lots of places, including his body and the bed. Also, I should note, one of the first tests he also asked us for was scratching an itch, which is another thing you might not think about, just how frequently we scratch itches, just subconsciously. I think he estimated he wanted to scratch an itch about 50 times a day, was it? So that's kind of, that's a place where robots also can help in what would be unexpected ways for a person without disabilities. So those were very prepared comments. These are his original comments. Henry can't speak, so he communicates by typing them out. And we were very excited about this. He said it hardly presses against him. He felt safe. He liked it. And it seemed to just wriggle around these obstacles. So I'm going to wrap things up here so I can have time for questions. This is just sort of a summary of what we've done with Henry. And the statement I would make is that autonomous mobile robots have the potential to give motor impaired users greater independence and serve as general purpose assistive devices that deliver affordable 24/7 personalized care. And I consider this work to be a really nice proof of concept. The robot is a commercially available general purpose mobile manipulator. It was not made for healthcare. This is actually in his home in California. We're able to automate a lot of his home and enable him to actually, for the first time, open his refrigerator, or at least open the refrigerator under his direct control. Able to, through this tactile sensing based research, help him while he's in bed to do things like pull up a blanket and wipe his face, grab a cloth, and then when he was in his wheelchair in his living room, do an everyday task, one of these activities of daily living, in this case, shaving himself, which falls under hygiene. So I think it's very promising. My perspective is there are lots of ways in which we can improve these systems, not the least of which is giving robots more intelligence about the forces that are appropriate given certain types of assistance. But I think it's very much a feasible path forward in terms of providing beneficial assistance. And more generally, hopefully I've convinced you that assistive mobile manipulators are an emerging technology with the potential to improve people's lives, and that intelligent control of applied forces across the robot's hands and arms will be a valuable capability. And with that, I'll conclude. We owe a lot, of course, to our funders, including most recently the Department of Education through a NIDER Center, DARPA, NSF, a number of companies, Coulter Foundation, and I'm very grateful for that. And of course, great credit to the many lab members and collaborators who made all this possible. Some people choose to have lots of pictures. I'm always afraid I'll miss somebody because there are so many people to thank. The best way to thank them, or for you to give proper credit, would be to go to our website, look at the papers, cite us. So that's it. I'm happy to answer your questions to the best of my abilities. Thanks.
So it looks like we've got 5 or 10 minutes. Do you have any questions for Dr. Kemp?
Yes.
That was a really fantastic talk. Absolutely great. My question is about...
Now I'm totally off balance, by the way, so you can hit me with anything. I'm like, floating in air. Bam!
My question is about the tactile sensing you talked about. So you have to have the ability there to not just sense the force, but to be able to spatially localize.
That's true. Absolutely. Yeah, I actually have a slide on that. So this is, I would not claim this is the best sensor technology by any means. This was enough for us to do what we wanted to do. And with sort of in-house, we developed this. As an aside, I'll say one of the interesting things about tactile sensing is unlike vision and unlike audition, there are not good technology. It is not a mature technology, right? For whatever reason, humans like to communicate with each other. They like to take pictures. They like to communicate sounds. But we don't seem to be so interested in giving each other great fidelity of what this door felt like, or, oh, the texture here. And so unfortunately, tactile sensing has not had the great benefit that these other sensing modalities have had in terms of these consumer products and highly evolved technology. So we had to kind of make our own. The way this works is that you have a conductive layer of fabric in the middle, then you have insulating, actually, let me take that back. You have conducting fabric on the outside and on the inside, and then you have a resistive layer in the middle, and that resistive layer of fabric, when it's compressed, the resistance goes down. So it's what you would call a force-sensitive resistor. And then we also put an insulating exterior on this. This shows the sort of the back plane. This is just a big conductive layer. But this is the inside, and you'll see that each of these conductive patches is surrounded by an insulating area. And so this region right here is the spatial region that will be sensitive. That is the tactile. And it's pretty coarse. One of the things that's, yeah, and I think that's kind of an interesting thing in a few ways. So one thing that I think is kind of cool about this particular technology is that we literally, we use a laser cutter to cut it out, and then we have a sewing machine. And once some students in my lab have unexpectedly become experts at sewing as part of their graduate careers. And but one of the nice things about that is it allowed us to rapidly iterate. And we started with very coarse, large tactile sensing regions. And over time, they became, over here, they became fairly, fairly small. So it's relatively high resolution. This is less high resolution, although one of the main changes was to add these taxels. That's what we call these tactile sensing elements, these taxels. You can think of like a pixel in terms of video, at the edges, at the corners. And then interestingly, for the upper arm, it actually has just one taxel, two taxels, three taxels, four taxels. So we haven't had an occasion to go back and revise that and make it, and I wish there's a slide, I wish, if we have more time at the end, I'll show you, there's an interesting slide that when we did that simulation work, looking at, trying to achieve poses, we found that the limiting factor, it pretty much, where the problem was in terms of why the robot couldn't achieve a desired pose, tended to be more frequently, the frequency increased as you were more distal on the arm. So there's something going on there in the sense that I think, and you see this in biology too, there tends to be higher resolution and it gets lower resolution. And we started looking at maybe how we might be able to model that, but it's something that comes out in practice too. Contact more frequently happens as you're more distal on the arm, and by having greater resolution, the robot can be better able to intelligently maneuver.
But there is a technology for sensing force and position, right? And you have it on your phone, and I have it on my computer, which is you touch the screen. So.
Well, so that can sense position, and they're actually, yeah. So capacitive sensing, that's a form of capacitive sensing. There are a lot of challenges with that. In fact, we do have a capacitive sensor on another robot. At least for the phone technology, it really depends on the material. Some materials it's not going to really work, and the other is it's sensing really a location or the area of contact as opposed to the force. So you could say, for some types of materials, you could say I am making contact.
But could you combine that with this so you would know, okay, I'm getting this much force in this patch, and here's where the centroid of the force application is, right? So it's kind of like best of both worlds.
Maybe. I'll say, one statement I'll make with respect to tactile sensing. Not only is it immature, but it's one of these areas where if you want to make an academic contribution, it's extremely challenging. Because there are these thousands of papers of people having various little technologies, many of which have not been tested very well, and the comparisons they're not really compared against one another. So it could be, and that might be feasible, but it's hard to tell, and it's also, I would just say, beware if you wish to conduct research in that area.
Start the field out, Charlie.
Yes, in the back?
Thanks for your presentation. So the question I had was, how do you allow the robot, obviously free range of movement, and specify sort of like dangerous positions to avoid tip over or basically the robot compromising its like
So yeah, so that's a really good question. For these particular types of robots that we work with and that we have worked with, I don't. Yeah, that was not the way to go, but there it is. So for all of these, they're what we would call statically stable. And they really, this robot can, especially this robot, it's over 400 pounds maybe. Most of them, and the center of mass is extremely low and has what you call large support polygon. So first of all, it can put its body in any configuration. It can move at whatever velocities it can achieve, and it is definitely not going to budge. It won't tip over. More than that, I mean, you would be very hard pressed to apply enough force to actually make it unstable. And that's true. This robot, it has all these batteries. It's extremely heavy down here. It would be easier to make unstable. Same sort of thing here. These wheeled robots and most wheeled mobile manipulators you find would be are statically stable. But there is a whole nother class of robots, which are robots with legs, which do have potential, long-term they have potential advantages. They also have a huge number of complexities, not the least of which is what you're bringing up, is that if your robot has a bug or it's losing power, it could fall. And it could, it's going to fall to the ground due to gravity, and it could hurt somebody or something. So it's an interesting, I think in the evolution of robots, I do expect even inside for there eventually to be legged robots because there are advantages, but I think it's a lot farther out than just having wheeled, statically stable mobile manipulators. Other questions? Yep.
So, just give us a perspective, where in the evolution is this? Are we sort of nascent, very, very young, or is this going to evolve in 2 years and we're going to see this, like I said, not just Henry, but 50 or 500?
Well, I think 2 years would be, 2 years is probably a bit short. 10 years might be about right. But that prognostication, beyond saying that this is feasible and I think it will happen, in terms of the specifics on years, I can't tell you. And a lot of it depends on commercialization. If society decides collectively, through the invisible hand, that this is really important, it will happen sooner. And right now, actually, society does seem to be saying robotics is important because there is a lot of activity in the startup world. So I think that bodes well for the future. Google, for example, acquired a whole bunch of different companies recently and is investing heavily in this area. So I think it's quite promising. But not 2 years would be too short. 5 years, maybe. 10 years, it could definitely happen. I would be very disappointed if in 20 years this sort of technology is not widespread and people aren't benefiting from it. That would be a surprising outcome, and I would be disappointed. So, does that do it? All right. Yes?
Do you do anything with voice recognition that I could just tell my robot?
It's a good question. Interestingly, we've done a lot of research with people with ALS and with Henry, who has had a brainstem stroke. And for people with ALS and for Henry, speech is really not much of an option. They tend to lose the ability to speak, and it's also, even for people who are earlier on in the progression of ALS, the speech changes in ways that it can be more difficult to automatically recognize it. But we've also done work with older adults, and certainly speech recognition is something that they're interested in. But it's also one of these classic things. It turns out that in the history of these sorts of user interfaces, that's kind of the knee-jerk thing people usually say. If you give them the option, they'll say speech recognition. But in practice, people often don't choose speech recognition. So we have various like Siri and other sorts of speech recognition capabilities on our phones, and yet we don't use them as much as you would expect based on what people claim they would want. And I think that's for a variety of reasons, not the least of which is, as good as it is, it's still frustrating in terms of its performance. I have an Xbox One, and I just want to rip the Kinect out because it gets things wrong all the time. So, but I think long term, it's technically a challenge. And it turns out that there are other ways for us to fortunately, there are lots of other ways for us to communicate with robots to get them to help us in the ways we want. From just a standard point and click interface like you saw Henry using to more exotic things like a point and click interface for the world, laser pointer. Being able to designate a location or a region is a very powerful cue, and that's something that we can do with robots more precisely than we could with language, for example. Yes?
Can you comment on the quality and robustness of the signal you were able to get from these tactile sensing skin or the piezo-resistive fabric you talked about?
Well, I'll say one of the, at least with this particular technology, one of the challenges is that it's not pressure, so it's not really in pascals. It's not force, it's not really in newtons. It's really a function, it returns a function of both really it's a function of the distribution of force, but assuming sort of symmetry, it's a function of like the contact area and the force that might do it. But anyway, it's a non-trivial, we can't back at, once we get that sensor value, we can't exactly say this is the force or this is the pressure. And we have some work in a paper where we put the robot in an instrumented environment where we had force torque sensors underneath obstacles. And we were able to show that if it's controlling this signal that's not quite pressure, it's not quite force, it still results in the robot limiting or reducing the forces of contact. But it would be nice if it were actually just a nice linear response in newtons, for example.
But you would say it's good enough for what you want to do, or how do you, from a requirement standpoint, what would you like to see in this fast evolving field of piezo-resistive fabric?
I mean, what I would like to see, so okay, this could be a much longer thing, but it's one thing which, there's this interesting thing that people have brought up, like there's this program manager at DARPA who talks about tactile sensing is a bit like battery technology. You see these big headlines about something that's going to be this new revolution in tactile sensing, and those innovations rarely make it, out in terms of a product. And one of the reasons for that probably is because it's not, you can try in your research to optimize one little number, but the reality, the success of that technology depends on a lot of factors. It's a multi-objective function. And so, for example, one thing that's not emphasized as much in research, although I wish it were, was just covering large areas. Actually don't need a super high, I would argue that robots don't need a super high tactile density. They don't need high resolution. They do need coverage. Another example of something that has been relatively neglected, although we showed some results in this, is like at articulated joints. You don't just make contact with the parts of your body that are approximately rigid. You also make contact at these articulated joints. And if the way that you want to do sensing on that is by covering it like skin, then you're going to have deformation of the surface. And that means stretching, right? You have stretching, you have bending. And it turns out that a lot of sensors, tactile sensing that's been developed, really only works on rigid parts. So you can try to design the robot so that it's just rigid parts that are covered, but having a surface that covers it has some advantages, and that turns out to be hard. So it would be nice if we had sensors that don't give, another problem we've had, false positives. Sometimes the fabric gets sort of misaligned, and it can register that there's a contact when there's not. So examples of things I'd want coverage of large areas, inexpensive coverage of large areas, easy to attain, which probably means it's relatively easy to manufacture. I'd like to cover articulated joints. I'd like to have a low rate of false positives. And it would be nice, although it's not necessary, to have either the pressure distribution or the force, some physical units where it's more clear what it means from an engineering standpoint. Those are examples of some of the things. But I think doing all that and making it low cost, it's one of these interesting things that sits between research and academia and product development and actual commercialization to really do it right. Did that answer your question? Okay. I know we're out of time, and so many of you probably want to leave.
So if you have further questions, feel free to stick around. But yeah, in the interest of time, we're running over, so we should probably thank our speaker again.